Greetings, ACT specialists. We've got an urgent solo mission coming up, and so I wanted to make sure that we're prepared for you and that you have every resource available to you in order to be successful on that solo mission, as well as the number of smaller tasks that are coming up to help ACT succeed. So we've been learning about gas laws, and one of the things that I'd like to do with gas laws is to know how much gas I can pack into containers, all right, so that I can ship them off to different places. So right now, we need to send 789 grams of fluorine gas to Triton. Triton is a moon of Neptune, and we want to try to fit this into a 300-liter tank. All right, so we don't want it to take up too much space. And right now, in the lab, the temperature is about 25 degrees Celsius. Here's the atmospheric pressure, and we're going to assume we're going to use the atmospheric pressure alone to try to pound this gas into the tank. All right, and try to fit into this 300-liter container. So my first question is, given these conditions, will the fluorine gas fit into the 300-liter tank? All right, I'm going to take a step back and I'm trying to visualize this. So I've got this tank, right, that's 300 liters. So here's my tank, that's 300 liters. And I'm trying to fit 789.0 grams of fluorine gas in there. And gas is kind of, it's hard to see, so we probably have the fluorine stored, and we're going to pump that gas in using 96,564 pascals. And I want to know if I'm maintaining that pressure, will all 789 grams fit? Well, the first thing I've got to figure out then is to figure out, hey, how much space does this 789 grams of fluorine actually take up at this temperature and at this pressure? And we know, okay, well, if I want to do that, I'm probably going to need my equation, PV equals nRT, the ideal gas law. And remember, the ideal gas law is just an estimate. It assumes that the molecules don't interact with each other and that they actually take up a very small amount of space relative to the space of the container. So two important assumptions there that we're making, but it's a fairly okay prediction and good enough for us to get some value out of it. And I'm looking for the volume that the fluorine will take up. So the first thing I actually want to do is to try to get my volume on the same side. So I'm going to do a little bit of algebraic manipulation. Yay, algebra, helping us out here. So now I've got the volume is equal to nRT over P. And what I'm tempted to do, I'm like, hey, I know the moles is 789.0 grams. I know my constant R, which is 0.08206, where the units are, let's see, looks like ATM liters, Kelvin mole for this one. All right, I plug that in there. I've got the temperature, 25 degrees Celsius, and I've got the pressure, 96,564 pascals of atmospheric pressure. So it seems like I could take my calculator, plug those numbers in, and I should be okay. But notice that, my units don't match up. And so I've got to have consistent units. That's super important. And so I've got a little bit of work to do before I can get there. So it looks like I don't actually have my moles. This is in fact grams, but we're not far off. So the first thing I'm going to do before I could plug in is to find the moles. So let's think about this. I've got 789.0 grams of F2, and this is review. You know how to do this. We're trying to get to the moles of F2 here. So I'm thinking, how do I get from grams to moles? Well, I know I'm going to need to cancel the grams, put the moles on top. Now, where do I get that? Right, the periodic table. If I look for fluorine on the periodic table, I see, 19.00 grams per 1 mole. But wait a second, I've got 2 of those, so I actually need 38.00 grams of fluorine are in 1 mole of fluorine. Take my calculator, take that 78.9, multiply by 1, divided by the 38, and I get 20.763 moles of F2. I'm tempted to write that down, but I realize I've got 4 sig figs, so of each, I'm multiplying, I'm dividing, so I can keep the lowest number of sig figs, which is 20.76 moles of F2. So I've got that. All right, I've got that calculator. Now the next thing that I want to do is I've got my moles, I could plug those in. I've got my R, those are incorrect units because that's the constant I'm using. Now I've got to take a look at temperature. All right, so I've got to find the temperature. Currently, Right now, I'm at 25 degrees Celsius. I don't like that. I want to be in Kelvin. And I know that the Kelvin is just equal to the Celsius plus 273.15. You have that on an important document. So I'm going to take the 273.15 plus the 25. So I got the 25, plug that in there. And so that's going to give me 298.15 Kelvin. Now I've got the temperature. And the final thing I just got to adjust is the pressure. I've got Pascal, so I'm going to need to encroach on my next problem a little bit. I'm going to find the pressure. To find the pressure, I'm thinking, hey, I've got 96,564 pascals. I'm trying to get to ATM. And to do that, I'm going to need to cancel the pascals to get to the ATM. And I know in one ATM, there's 101,325 pascals, or 1.01325 times 10 to the 5th power. And if I put that into my calculator, I've got 5 sig figs as my lowest number. I'm going to get, I'm going to be able to fit it here, 0.95301 ATM. So now I've got all my values. Let's summarize. I figured out the moles here. Okay, I've got my temperature in Kelvin, and now I've also have my ATM of pressure, so I'm ready to go. I'm ready to finally use this equation here. So I'm going to go back. I take my V, that's equal to the number of moles, which is 20.76. I'm going to, for the sake of space, leave out the units, but remember they're there. They're important that they cancel out, and we see our units match up, so that's good. I need to multiply by the temperature, 298.15. Oh, I missed the R. I'm sorry. I need to go back and put the R in, but multiplication, doesn't matter which order you do it in, so luckily I don't need to erase. 0.08206. And now I'm going to divide that by the pressure. And the pressure I determined was 0.95301. And so if I plug that in, I end up, let's see, 20.76 times 298.15 times 0.028206 divided by 0.95301. And I end up with 532.96. Okay, but one thing I forgot to do is when I added this, my Celsius was actually 25 degrees. So I need to go back and remove these two sig figs, because when you add, you've got to keep it to the least precise unit, which is the units digit here. And so I'm actually only have 3 sig figs here, and that actually changes. It could change the result a little bit because I'm a little bit less precise now than I was before, but it still seems like 532.69, so I'm going to round that to 533 liters of F2. So normally, at these conditions, fluorine would take up 533 liters of space, which will not fit into that 300-liter tank. So in part 2 now, I'm going to have to figure out something that works to fit that all in. All right, so I want to think about, hey, what are the options? Well, I'm trying to squeeze a bigger amount of gas into a smaller, right? I'm trying to pressure that in. So one thought is, you might think, hey, why don't we just increase the pressure, right? Let's increase the pressure and really just squeeze all the gas into the container. And that seems totally reasonable. All right, the other thing that I could do is, well, these molecules are moving up very quickly, and that's why they're taking up so much space. I can decrease the temperature. That'll cause them to move slower and also decrease the volume as well. So I could decrease the temperature. That seems reasonable. And the third thing, well, maybe I'll co-opt those guys on Triton and say, hey, in 300 liters of space, I cannot fit this many grams of fluorine. You're going to have to take a cut. And so I could actually decrease the amount that I'm going to add. So decrease the amount of fluorine that I want to put into the container. And these are all legitimate things that I could do. All right. Now, what standard is this hitting? These are, problem 1 is hitting, well, let's not worry about the standards, but let's think in the first problem, I had to know conversions between pressures, between temperatures. I need to remember how to convert from grams to moles. In the second part, I need to have an intuition about what I can do to pack gases into a smaller container or a bigger container. All right, so now we're ready to go to the second part. And to do that, you can take a look at the next video.